Right, good morning, everyone. Sorry, I'm just trying to get my screen sorted out here. I'm not sure I'm sharing the right thing at the moment. Hang on. So there we
I
go.
don't see anything sharing at the moment.
No, that's right. Okay, can you see
now
it now? Yeah, and hopefully now you see it full screen, yeah?
Yes, perfect.
Very good. Okay, good morning or good time of day, everyone. Yeah, so this is the second lecture on kind of measurement in Monte Carlo, or how to make and use model independent measurements, essentially trying to give you an insight, if you're a theorist, into writing Monte Carlos, into how experimentalists do, or at least should, make use of the tools you provide. And for those of us who are experimentalists, just raising some of the issues involved with that and trying to suggest solutions to some issues. But I guess the main, as I said yesterday, the main point is to raise the issues to make sure you think about them, because often they're the only really wrong thing to do is to not notice the issue at all. And often there are multiple ways round, or ways of dealing with the kind of issues I'm talking about, which are mostly to do with model independence and how you might try and correct for detector effects. And the main wrong thing you can do is just not to say what you did. Often there are multiple well-defined ways of addressing these issues. There are some which are clearly better than others, and I'll maybe go through some of those in this lecture. So just to recap where we were after yesterday. Oops, that's not. Yeah. Just to recap where we were yesterday, the summary so far, I gave some kind of introduction to how Monte Carlo event generators are used in data analysis, and how that couples actually with the full simulation of a detector in Géant. And also how various particles are reconstructed in the detector, in the data, and the importance of correcting for these detector effects, because if you don't correct for the detector effects, then any comparison to theory will need to actually implement those detector effects, and that is typically a very time-consuming and specialized thing to do, and it's also the kind of thing that 20 years or even 2 years after a measurement has been made, it may be very difficult to actually recover the exact conditions that the detector was under at the time, and feed some new theory prediction through it. So correcting for detector effects is important, and the red line at the bottom of here, which I didn't get onto, which is what I'm going to discuss now, is the dangers of overcorrecting, essentially of extrapolating into unmeasured regions. And often when you read a paper, I think now when you read a CMS or an Atlas paper, it will be fairly clear the difference between correcting for detector effects within regions that have been measured and this extrapolation for what we would more typically call acceptance effects. In older papers, it's not necessarily so clear, and we may not even get it completely right every time these days. And I want to alert you to the issues involved there. So what I mean by this correcting for acceptance effects is extrapolating outside the region where we measure into some full phase space. So for instance, if you have a trigger selection that requires that jets have a PT greater than 20 GeV, or that electrons or muons have a PT greater than 25 GeV, you may decide that actually you have a fully inclusive calculation you want to compare to, so you're going to extrapolate away for that. You're going to use the Monte Carlo to remove that cut effectively, and to go down to PT of 0. Or likewise, you have a pseudo rapidity selection which matches your detector acceptance of about 2.5, which is typically where the barrel calorimeters may extend to. And actually, you didn't want to have that. You want to extrapolate to the full phase space. Now, that's a kind of, in some cases, that's a sort of unavoidable thing to do. And you may say, well, the total WW cross section is a good one, is dominated by stuff you would see maybe, and it's an interesting number to extract. I'm not that interested in placing an angle cut or a PT cut on my leptons. I'd really rather just have the total WW cross section, and my mate, this theorist, has just calculated it next to leading order, so I want to compare to this fully inclusive thing. That's a legitimate thing to want to do as a scientist, but you have to remember that actually you haven't measured that cross section. What you've done is you've measured it within a region where you have a detector, and then you've extrapolated to the full phase space. And that extrapolation builds in some theory expectation. You're essentially using, in the regions where you have no measurement, you are actually just using the theory to recover that bit of the phase space. But anyone can actually do that. If you've measured the cross section within a fiducial region, so within that, say that PT greater than 25 and rapidity less than 2.5, if you've measured the cross section in that region and corrected for detector effects within that region, so it's effectively a particle level cross section in that region, then anyone can do the extrapolation. You don't need the detector simulation. You can take a Monte Carlo, you can say, what's the cross section in the restricted phase space? What's the total cross section? I'll just correct by the ratio, and there we are. So you can do that, but of course you're buying that Monte Carlo to do that. So that result will depend on whatever assumptions or whatever accuracy and precision that Monte Carlo has in the region that you didn't measure. And we really must be careful, because we have to remember we didn't measure that region. So in general, it's a really bad idea to contaminate the data with the theory we're trying to compare to. A good practice really is, even if you want to do this extrapolation, first of all, measure the fiducial particle level cross section. And then you can have a discussion part as an experimentalist. You can have a discussion part in your paper where you say, okay, I've measured this thing, which is as model independent as I can make it. And now I'm going to use some theory to extrapolate it into different numbers to do some interpretation, essentially. That's not a bad thing to do, but it is a bad idea to mix the two. So it's a very bad idea to do, say, the detector correction to particle level at the same time as you do the acceptance correction, all in one go. And then no one can ever untangle them, and you have essentially built in to your data whatever Monte Carlo you used for the extrapolation. So, right. So just to give a concrete example, for example, this paper here, we measured the total, we claim to measure the total TT bar cross section to be 177 picobarns in run one. So this is 7 TV data, but the measurement was actually, if you look into the paper, that's the headline number there, is the sigma TT bar. But if you look at, dig into the paper and see what was done, the measurement was made in the dilepton decay channel. So you're requiring that the both tops decay to W's, which decay to leptons, electrons or muons, basically. They had a, excuse me, the phone's ringing. I'm just going to have to stop for a second. Oops, good, all right. Yeah, so they made this measurement using the dilepton decay channel with PT greater than 25, rapidity less than 2.5 cuts, like the ones I mentioned in the previous slide, and various other cuts on things like missing energy or the transverse mass or the number of jets in the event. And if you drill down and look in the paper, only 1.7%, according to the Monte Carlo, only 1.7% of top anti-top events are actually used to measure the TT bar cross section. So 98.3% of the events are not actually seen. Now, some of that is detector efficiencies. Some of it is the branching ratio of W to leptons, but a large amount of it is extrapolation into a completely unmeasured region. So that what I mean by that, this is a kind of cartoon illustration of it. We have a measurement. This is now, once you imagine the screen is my full phase space at the LHC. I want to measure something, so I have a bit of, I have a blurry picture of it, and the blurry picture is because, you know, my electron resolution isn't perfect, for instance. So I can unfold for that, and I can correct back to within some uncertainty. I can recover what the particle level cross section was in that region. That's quite a limited region, so I'd like to measure a bit more. So I increase my acceptance. Maybe I find some smart trigger that allows me to lower my PT cut, or I build a new detector in the forward region and increase my acceptance there. That's great. Now I reach some point where, no, I can't actually go below this transverse momentum, or the beam pipe's in the way, so I can't go to forward regions, but I've got pretty much a good idea of what's going on in these events. These are TT bar events. We know what they are, so let's just use a Monte Carlo to extrapolate for the rest and fill in the gap. The problem is, which as I've already said, is how reliable is that going on? Now, not only is there how reliable is the standard model calculation there, and it may be, you know, at low PT, these things may be breaking down for some cross sections. We may have a very rapid rise in the uncertainty there. But even more worrying is, you know, we're measuring in collisions that we've never seen before, and it may be that there's something very weird going on in the region that we're not measuring. The weird thing in this case is my daughter was far too much suntan cream on, I think. But nevertheless, the point is that we're measuring. No one's done these collisions before. We've gone to a lot of effort to build the LHC and collide beams at these energies. And to make a bold assumption that we know exactly what's going on in some non-trivial region of phase space is actually wrong. I mean, in the end, reduce it to the bottom line, you're actually lying, because you haven't actually measured the total TT bar cross section. You've measured it in what we call a fiducial phase space. So the idea of the fiducial phase spaces would just to be honest about that and say, well, the regions you can see here are the regions that we've actually measured, and the region that's in white there is inaccessible and has been removed by kinematic cuts. It's not part of the cross section we measure, and those kinematic cuts then can be made at the particle level. So I described, how we define final state particles yesterday. If you apply these cuts at the final state particle level, then they're not really detector independent, okay? You're not requiring a theorist to simulate your detector. All you're doing is requiring them to apply some kinematic cuts at the truth particle level. So it's a halfway house, if you like. It builds in the fact that your detector has limited acceptance, but it removes the kind of expert-only stuff about exactly how efficient and what the resolution is within that acceptance. So that's the concept of a fiducial cross-section, which in well-written experimental measurements you will see discussed usually quite clearly. You'll see a lot of experimental cuts applied, many of which may depend on the details of the detector technology, for instance. But hopefully at some point you'll see a little table saying all the cuts have been corrected for into this fiducial region, which is where I actually make my measurement. Are people having problems with the slides? Can you see the slides now? Okay.
Yeah, I'm sorry, I just see a corner of the slide, but this will be my computer then. Sorry.
Okay, well, good luck. I hope you managed to recover it. The slides are actually uploaded on Indico, so you could always go through them yourself there if you're having trouble. I can say I'm on slide 14 at the moment, if that helps. Okay.
Thanks.
So, so this idea of a fiducial phase space is a really important concept. You're basically saying that irrespective of detector efficiencies and resolution effects, there are regions that we don't measure at all. We don't have 4 pi detectors. We can't go down to 0 PT. So we define a set of I've already said this, but I'm just reiterating it here because it's really quite important. We define a set of selection criteria that can be applied to the final state truth particles, now not to detector objects, not to electromagnetic clusters or whatnot, but to what we think is a true final state electron. So we've done some work in unfolding to a true final state electron from whatever our detector readout was, but we're only doing that in the region where we have a detector. And it was quite unusual, quite radical very early on in the LHC measurement program, so back in 2009-10, where we started, the first measurements we made were what we call minimum bias events. And minimum bias is, it's supposed to be, as it says on the tin, it's supposed to be the kind of most open selection you can possibly have. So it's completely dominated by soft QCD scattering. And it's a very important measurement to make because that kind of characterizes the background in PP collisions at a certain energy for the first time. And it's something that had been it was part of the mythology of hadron colliders that everyone measures minimum bias and then we try and tune the Monte Carlos to it. But if you look back at the minimum bias measurements from things like UA1, UA2, and even the Tevatron, they didn't really specify what minimum bias was. They try and correct to something called, what was it now? Non-single diffractive measurements, which is they're trying to say that they know there's a class of diffractive events that they can't really measure, that fully diffractive events don't even appear, that single diffractive events have a different acceptance, and what they want is the inelastic collisions. But that was usually defined by some detector level cut that was very hard to translate into something you could use in the Monte Carlo. And so there were huge uncertainties in tuning the Monte Carlos to try and model these events, because you basically couldn't tune without knowing what this bias was. Even if it was minimized, there was still a bias. And the only way of implementing the bias was often at the detector level, and you didn't have access to the detector simulation. So when Atlas and CMS did this for the first time, there was quite a lively discussion about that. And there were statements that would say things like, okay, minimum bias is something with a true particle with at least 300 MeV within this rapidity region, and that's what we mean by minimum bias. And if your simulated event has that particle in it, then you can use it, and you should use it to compare to our data. And if it doesn't, then you shouldn't. And that was quite a breakthrough. In fact, we went back and re-implemented at the Tevatron to some extent as well. It was used very, very heavily in the tuning of Monte Carlos in the early days of the LHC. It's one of the reasons why we were able to do that better. So many, but not all, theoretical predictions can apply these phase space cuts. And if you can do that, that's the gold standard, right? Because then you know you're comparing like with like, and reliably compared to the region. And in particular, of course, in the context of this school, Monte Carlo, any prediction which is implemented in full final state Monte Carlo, you can definitely introduce the fiducial phase space cuts as I've described them. If you want to compare to a theory prediction that can't do that, and there are good reasons why some cannot, you can get more precision. The typical reason is that if you integrate over the full phase space, it's easier to get a higher order correction. There are simplifications in doing a higher order calculation, or a resummation, for instance. If that's true and you really need it, then what the experiment should do is first measure the fiducial thing at particle level and then provide an acceptance correction. And that acceptance correction will have to build in some other theory. But if you've done it in that way, you have good control over what that theory is. And if that theory improves, for instance, you can redo it even 20 years after the measurement. You don't need anything to do with you don't need the full detector simulation in order to do that. So these so this fiducial cross-section, again, probably from today's lecture, the idea of why we use fiducial phase space and what it means is probably the most important thing. And one of the things that's mentioned there on this slide is that it's defined in terms of final state truth particles. So it's worth saying, going back and revisiting what these are. This slide's a bit of a mess, but it's similar to the one I showed yesterday, that we have electrons, muons, taus, neutrinos, quarks, and gluons, which manifest themselves as hadrons and or jets, photons, and then the business of the WZ and the top, which are not final state particles. There are some choices involved in all that, so we tend to, we tend to define stable as being. Oh dear, it's a bit of a mess. Sorry, I should have checked this was doing its. Yeah, so that the we have to make some decisions about where we will treat things as operationally stable. 30 picoseconds tau proper lifetime is a common one, which leaves you, if you look at the lifetimes of some common particles, it leaves you with the charged pions, as we discussed yesterday, being treated as stable, with the K short even being treated as stable, and of course the K long for sure. But with B mesons often being treated as unstable, even though 2 millimeter resolution is the 2 meter resolution is okay. Sometimes to actually identify a B0 decay vertex, we often still treat them as unstable, and the pi 0 would clearly be unstable. I don't know why it says 3.6 meters there. I think something's gone wrong with the font there. But the the lifetime in picoseconds is correct there. It's very, very short, and it certainly won't travel 3.6 meters. You will not be able to resolve it at all, the decay vertex of a pi 0. Okay, so where will this slide move on? Yeah. So looking at what then that's fine in terms of what's stable and unstable, and at some level you could say anything I treat as stable is a final state particle, but there are a few more issues that one has to consider, and I'll just go through a few of those here now. So you might think that the simplest of all of those guys was the electron and the muon, but there are some issues to discuss. Some of these we covered in the tutorials last night. Electrons and muons from hadron decays. If you're looking for what you want is a prompt electron or muon, then you want to remove those. They will be typically removed by applying some isolation cut. You also have hadronic decays that don't have a true electron or muon in, but can appear as though they did in some cases. So you can define prompt leptons as being leptons that don't come from hadron decays. You may, in some analysis, of course, want to measure the leptons from hadron decays, and we can do that too. It's a decision you have to make. That's quite a robust and model independent way of distinguishing between two classes of lepton. it's more model independent than asking if the lepton comes from a certain propagator, for example, in the hard process. You can implement this in tools like Rivet, which I hope to come across in the tutorials already. But you may also need to implement such a distinction in your experiment software. How does your experiment keep track of the truth record in a Monte Carlo event? What is it you're actually unfolding back to there? Again, there's no super right answer here. It's a matter of, these are just questions you have to ask yourself when you're designing an analysis. And if you do want to select, for instance, the problem leptons, so leptons from a W or a Z decay rather than leptons from a J psi or a charm or bottom meson decay, then you probably want to introduce some isolation at the detector level, and then you may want to implement the particle level isolation in your fiducial phase space as well. It depends, you know, do you want to apply an isolation criteria from jets? Do you want to do that at the particle level or not? If you don't, you're paying some price in terms of model dependence. So these are all issues that one has to think about. Another issue associated with electrons and muons is that they will emit final state photon radiation, and a lot of it actually is in the collinear limit, especially electrons, because it depends on the mass of the particle. So it's somewhat suppressed for muons, but it's not very heavily suppressed at all for electrons. And then you have to think about how are we actually measuring these guys in the detector. So muons, we typically measure the charge track. You will see the muon leave a charge track in the inner detector. It will probably leave minimum ionizing trail through the calorimeter and then be measured in a tracking detector on the outside. So any photon radiation that's lost there, that you will see it, you know, the muon's energy as it propagates through the detector will be slowly decreasing because it will radiate probably a photon or two on the way, some of them quite soft maybe. Those will be lost. So the curvature of the track will not include those because they'll have been radiated. And usually that, I mean, I'm not talking about photons radiated through the interaction with the material. I'm talking about photons radiated essentially in the beam pipe from QED final state radiation. So the track will not include the energy of those photons. So if you're wondering what to compare to in a calculation, you probably want to take into account that some energy has been lost that way, if you can calculate the final state radiation. For electrons, we would typically cluster the calorimeter cells together. So we're not, although it will leave a track, we usually don't use that. And part of the reason for that is that the electron will also interact with the material and radiate too. But typically we will measure the energy by looking at the calorimeter cells and electromagnetic energy deposit in the calorimeter. Now, if there's a photon, as you see in the little diagram there, if there's a photon, that dashed line been radiated very close to the electron, then it may well be included in the electron energy, because it may not, you know, our cells have a finite size, so it might even be in the same calorimeter cell, or it might be in a neighboring one that is clustered together with it. So you need to make decisions about what you call, how you're going to treat this final state radiation. It's a significant effect, particularly if you're looking at the impact, whether you have a resonance like the Z and you can get radiative returns and things from the Z. So you have a huge cross section at the Z peak, and that will contaminate the mass distribution around it because of this final state radiation. So we can define lepton momentum as what we call born leptons, which is the basically zeroth order QED final state. So it's as though we just have a magic wand and we turn off final state radiation. That's obviously not what we actually measure, and in principle it's not actually measurable because there's infinitely soft radiation is always possible. However, you can get very close to it if you want, and final state radiation is quite a well understood effect in the standard model. So if you're prepared to buy that model assumption, then you can calculate something that we call a born lepton, but you have to remember it's not what we measure. It's something you've added a theory correction on top of what we measure to get that. You could also measure bare leptons, which is after all the final state radiation, so it's whatever's left, and that's kind of closest to what we actually measure in the muon. Okay, so the muon, we're measuring the track. The final state radiation, the significant part of it will have happened before it leaves the beam pipe. So we'll see the track, and we'll get what something looks like a bare lepton. It's a little bit more dodgy for electrons because the cloud of virtual or very soft photons around it is much bigger because the mass is lower. So probably the most rigorous final state type definition of this is what we call dress leptons, which is where, and now remember, this is at the truth level we're talking about. This is not a detector thing. This is how you define the cross-section at the final state particle level, where we take all the photons that are close by and we cluster them into the lepton momenta. So it's getting very close to a jet finder, which is the way we treat QCD radiation in the final state. And it's a much smaller effect than a jet finder, but essentially it's getting close to that idea, where you take the charged particle and you sum any electromagnetic energy, any photons around it that came from the hard process are clustered there. This may sound quite finicky, but as I say, these can be 10-20% effects in some regions. And also, if you're measuring a cross section, for instance, like E plus E minus, maybe you want to measure the Z plus gamma cross section in some sense. What you're really measuring is a dilepton plus a photon cross section. You need to make some decision when is a photon actually separate from the lepton, and so in principle you will have an angular cut there already. So all this is doing is systematizing that and making it more rigorous and making it reproducible. Various different criteria can use to cluster, but the important thing is to use one that you can also implement at the final state particle level in the theory. So you probably need to speed up a bit, sorry, but there's a whole bunch of discussions around which is the right one to use in which circumstance, and in principle, because final state radiation is different between electrons and muons. If you actually want to produce a combined cross section where you assume lepton universality and combine the electron and muon measurements to give you a W or a Z measurement, then you may have reasons to go back to the bare level, because you know that the FSR is different between electrons and muons. But we know electrons are not equal to muons, and actually if LHCb is right, then they may be rather significantly different in interesting ways. So it's probably better to measure the electron channel, the muon channel, and publish the correlations between them, actually. Final state tau, we can tag these, at least some fraction of them, when they live long enough. The final state particles are electrons, muons, and neutrinos for lepton decay. So you can define the fiducial phase space in those. Initial issues are essentially the same. Hadronic decays, the final state particles are hadrons, which can be clustered as jets sometimes, and again the neutrino. Such a definition alone can be complicated, because there are a lot of hadrons in an event not from taus. That's not an in principle problem, but it's an in practice problem in the detector. And you will typically have experimental cuts to reject backgrounds based on jet multiplicity, jet mass, things like that. They can be hard to replicate at the particle level. Sometimes it's better to require a hadron in the jet to have come from a prompt tau, which is not really a final state based thing. There's actually not that many particle level measurements of tau leptons produced at the moment, and this is a very kind of active area for discussion. It's actually something I'm working on myself at the moment. Final state photon, they're actually not that hard to define, but you almost certainly want to apply some kind of isolation criteria because of the kind of fragmentation diagram that you see on the right there. Where again the photon can be arbitrarily soft and collinear with the quark. So again, back to similar issues with the electron or with jet finding, you'll want some isolation criteria that you can implement in the theory and in the detector. And you may also want to say define prompt ones so that you're only looking at photons that come directly pre-hadronization, so you exclude the photons from, for instance, pi0 decays, which is a very copious source of photons. So those are physical definitions, and you may want to define a phase space that incorporates those at the particle level, so that you have some idea. The theory will include both those diagrams that you see there, for instance, but there'll be a collinear divergence in the fragmentation contribution. So the theory must apply some cutoff between the quark and the photon, and you want to mirror that as effectively as you can in the particle level definition, and then mirror the particle level definition as closely as you can in the detector selection that you use. Final state neutrino is it's a very obvious thing. You may not know what flavor it is, but you know what a neutrino is. But experimentally, of course, it's not measured directly in the detectors. So, in fact, to resolve exactly what you mean by a neutrino, you obviously have to define missing energy, and then in order to do that, you probably want to measure the electrons, the photons, the taus, the muons, the jets, and anything left over, as well as you can, and then do the negative of that, and that will be your definition of your missing energy, which is the best guess you have as what a neutrino might have been doing. And worth remembering that, of course, if you've got dark matter production or something else going on, that will be indistinguishable from a neutrino. Final state partons. Partons radiate. A lot of the issues that are the same as with the electrons radiating photons, for instance, but much more so because of the strong interaction and because of confinement. So partons radiate more partons which hadronize. So we, in the end, run a jet algorithm on these. On the final state particles, we form a list of those particles, which the particles that list can be a list of reconstructed particles or of true particles, or if you have a theory that only goes to parton level, it could be a list of partons. And you typically merge nearby pairs according to some distance parameter and iterate until you meet some termination criteria. All of those are decisions that are made in a jet algorithm. Typically, we use anti-KT algorithm now, but there are alternatives. And then the idea is that the energy momentum of the jet will represent at some level the energy momentum of the parton from the hard scatter. You do need to think carefully about what you include in that clustering procedure. Do you include muons? Do you include electrons? Do you include neutrinos? All of those can be produced from hadron decays. Some of them are produced in the prompt from the hard process directly as well. Do you want to distinguish between the two? All of these, again, seem like finicky issues, but as measurements get more precise, you have to be clear what decisions have been made. For instance, in a reconstruction code, an electron will be in the calorimeter, will often form a jet initially, and then you need to have some criteria about how you say, no, this wasn't a jet, it was an electron, I'm going to remove it from my jet list and include it. All of those things require decisions which are not trivial. They're often made once and for all in a detector, in a detector's code, but you need to be clear about what's been done if you want to reproduce them in a theory calculation. And the final, and then B-jets, a lot of the issues are the same there, but we can also tag them with some B-tagger, and that isn't as simple as you might think, because if you had a jet that was initiated by a gluon, it may well, for instance, radiate a B and an anti-B, and you may end up tagging those. So do you call that a B-jet or not? At some level in the theory, it's not, because it has no net B quantum number. But in the experiment, you may well, it has real B mesons in it, so you may tag them. Again, there's no absolute right or wrong answer. There are well-defined approaches to deciding what to do when you need to say what approach you did. So the last part of this, I guess I'll just go through a few examples. I have to apologize in advance to my CMS colleagues here. But these slides have been inherited, so I'm going to blame Emily for this, actually Emily Ness. But it turns out I have two good examples and two bad examples, and both my bad examples are CMS and both my good examples are Atlas. I've already used a bad example from Atlas in terms of that TT bar cross section, but that's not, I don't know, it's just bias, I'm sorry. Both experiments do good things and bad things occasionally. So this is an example of a W plus jet measurement from fairly early on CMS data taking. They define a fiducial phase space, which is great. They demand one dressed prompt muon, which passes the PT cut and rapidity cuts there, which means it's inside their detector. They make a transverse mass cut using the muon and the prompt truth neutrino, which is a proxy for the missing energy. All of that's entirely respectable. They have a well-defined jet finder. They exclude neutrinos and that muon from above, but they include other muons in it. They tell you what jet finder they use. All of those are great. They're very clearly defining the final state. And they demand that the jets then have PT greater than 30 GeV, rapidity less than 2.4. And they have in the fiducial phase space a separation between the jet and the muon. So all of that follows the data analysis cuts that they made at detector level very closely. They're all cuts that you can implement in the theory in Rivet, for instance. However, they then decide that actually they want to get rid of top events from these measurements. because obviously top decays are a copious source of W's, and they say, oh, we don't want to include those. We want to look at the continuum W plus jets. So in order to do that, they apply a B jet veto, because of course in top decays the W jets are the W's produced in top events are accompanied by a B jet, because from the top decay. So they apply a B jet veto in order to allow them to suppress that background and then subtract it. But unfortunately, they don't apply the B jet veto in the fiducial phase space. So that means that this fiducial phase space is absolutely fine if you only feed it standard model W plus jet cross-section measurements without any top in there. But if you feed it just any old event, and if you feed it inclusive events, for instance, or BSM events, or whatever you want, if there are B-jets in there, then they will not be correctly vetoed, because that B-jet veto was only applied at the detector level and isn't included in the fiducial phase space. This is a problem when you want to use it for reinterpretation in terms of other calculations. And in principle, it's a problem even for precision standard model calculations, because there will be virtual top events, and in the end, there is interference between single top and W plus jet. That's a very, very small effect, which is why in practice this measurement is still valuable and still useful for validating W plus jet calculations, but it's not valuable or useful for constraining beyond the standard model physics, and it has an intrinsic limit on its precision from the theory because of these interference terms. Now that intrinsic limit is a lot less, it will be a lot smaller than the actual experimental precision, so that's not really a terrible thing to have done here. But it's a little bit annoying, because they could have implemented that B-jet veto in the fiducial phase space, and then we wouldn't have had this problem in the first place. A little bit more severe is this electroweak W plus dijet measurement, where they make the analysis cuts that are shown in the green box there, which you'll see are cuts on the jet PT and the lepton PT, and then they define what they call a fiducial phase space in terms of the mass of the dijets and the jet PT, but not in terms of the leptons or anything else. They just demand it's an L nu plus dijet's final state. So there's a huge extrapolation going on there, which makes this of kind of limited use if you want to compare to a calculation, because you've built in you built in the current theory knowledge basically to extrapolate from the lepton and missing energy cuts to a full phase space in the lepton neutrino system. I showed a bad example of an early measurement of a TT bar cross section from Atlas, which in one case wasn't even corrected to particle level. It was just a detector level observation, and then the second one was extrapolated to full phase space. The more recent measurements, where we have more statistics and more precision, both experiments are moving away from doing that, of course. And here you see a nice fiducial cross-section measurement of the top, where it's actually the top is defined in terms of the final state. So it's not even correcting back to a full TT bar, it's defining it in terms of the lepton, the missing energy, the B-jet, and so on. So that's kind of nice. And even in Higgs, we know I said the Higgs is not a final state particle. You can't measure a fiducial cross-section in terms of the Higgs. But what you can do is apply a fiducial definition to the final state that the Higgs decays to, which in this case is a pair of photons. So this is a, quotes, fiducial cross-section of the Higgs itself. Well, actually, it's a genuine fiducial cross-section, which is quotes of the Higgs itself. So we've demanded two isolated photons with a rapidity less than 2.37 and a crack in there, which reflects the acceptance of the electromagnetic calorimeter in Atlas. We've made a PTI over PT gamma thing. That I is the charged particles of the energy in the isolation cone around a photon. So there's a particle level isolation criteria applied there, which can be completely reproduced in a theory. There are cuts on jets, there are cuts on the diphoton system, all based upon those selection criteria. And in the end, therefore, you can extract a fiducial cross-section, which is at first initially a diphoton cross-section, and then you can look for the resonant bump in that and subtract the background underneath it based on a fit, which gives you effectively a fiducial Higgs cross-section. So there's a lot going on there, but it's a brave and to a very large extent successful attempt to make a Higgs cross section as model independent as possible by defining it completely in terms of final state particles, which is what's done there. So that's kind of nice, and this is again increasingly done now by both Atlas and CMS. Again, I apologize for the bias in the examples chosen. The final topic I'd like to discuss is this business of background subtraction and what does that mean and whether we should do it or not. So the backgrounds in an experimental paper it's a word that will be used for a bunch of different things. There are fake backgrounds, which are what we call reducible. So that's, for instance, things like where I have say a jet that fragments weirdly and ends up showering entirely in the electromagnetic calorimeter and has only one track pointing to it, so it looks a lot like an electron, but there was never a real electron involved there. But just from the detector point of view, it's really hard to distinguish from an electron because there's just one track and it showered really early in the electromagnetic calorimeter as well. But it turns out it was actually a charged pion and a neutral pion or something like that together, between them faked an electron. Those are a purely experimental issue, and we have to get rid of them. They depend entirely, the level of those backgrounds will depend entirely on the geometry and the design and the calibration of your detector, or on the beam conditions at the time, if some of them are coming from pilot, for instance. So that's squarely in the experimentalist job. We have to get rid of those. There's no way that a theory calculation should ever be worrying about those. There are ones which are kind of a similar final state, which are in the gray area, and there I would class maybe something like you're trying to measure prompt photons, but you've got photons from pi zeros. So it's a kind of similar final state. It really is a photon, but it's coming from a different source from the one you actually wanted to measure. So it's coming from a hadron decay rather than from the scatter itself. And then there are things that are really an identical final state, and maybe I can go back to the W plus jet one there. And we did an example of this here. We were trying to measure in Atlas W plus B jets, and we had quite a discussion about, well, what do we do about single top here? Because single top is a W plus a B jet when it decays as well, but it's a different set of Feynman diagrams than the continuum W plus B jet. And in the end, we decided, it also became quite tricky for political reasons because we had a group measuring tops and a group measuring W plus jets, and actually they're the same thing at some level physically. So in the end, what we did was we made an inclusive measurement, which was W plus B jets without asking any questions, without subtracting anything to do with top, without asking whether there was a top involved in the event or not. And then we measured that at a particle level, and that was our most model independent measurement. And then because we did want to get some information on the non-top contribution here, because the single top had been measured elsewhere, we actually used the theory calculation to subtract the single top background from it, which is, then you're buying completely that theory calculation. It may be an interesting thing to do to interpret your measurement, but it's not actually part of the measurement. And I think that's the kind of issue that arises quite often. If you're measuring dileptons, if you want to measure Drell-Yan, do you include contributions from TT bar again? Because there will be dilepton events coming from TT bar. Do you include them or not? You have to ask those kind of questions. Or do you include leptons from taus, for instance? If you're measuring an inclusive muon spectrum, do you only want prompt muons, or do you want to include any muon that might come from a tau decay or from a J-psi decay? Some of these are similar final states, some of them are completely identical final states, and you have to worry about that. So I probably, now these little arrows are going to go through everything I just said. The first one should be just summarize what I just said. Fake backgrounds, the experimentalists have to deal with it within some systematic uncertainty. Identical final states, they will interfere in principle with the signal, so subtracting them is in principle unphysical. It can be interesting for interpretation, but it should never really be part of the measurement. And so I've got an example of one here, which is trying to extract electroweak vector boson fusion from W plus jet or Z plus jet production. And really the only thing that distinguishes, that, you know, they look like very different Feynman diagrams there, whether you have actually a vector boson fusion occurring or whether you have some other radiative events. But so this process can't be isolated due to the large destructive interference between electroweak Z boson, the Bremsstrahlung process and the vector boson fusion process. But you can define some bits of phase space where it makes a more significant contribution than others, and you can interpret then the cross-section measurement and extract information about vector boson fusion. But it's usually, I would say always, good to include an inclusive measurement where you make no assumptions or subtractions and then start interpreting it in terms of what processes you were particularly interested in the measurement. Again, as said, TT bar is actually WW plus jets, which is also lepton plus missing energy plus jets, really, or dilepton plus missing energy plus jets sometimes. And you need to be aware of that and decide what you're going to do about those different contributions. So it's, in general, it's dangerous to isolate certain Feynman diagrams. It's not a physical thing to do. Remember, they're amplitudes, not cross sections. So in some cases, it's a reasonable approximation, but you've got to treat it with real caution, and always better to try and draw the line between and have an inclusive observable first, and then maybe mix up some interpretation in there as you try and extract more information from it. And then a similar final states, soft QCD is probably the place where this becomes really horrible. If you're looking for diffractive events, for instance, and I mentioned this in the minimum bias definition, you have color singlet exchanges and non-diffractive exchanges, and you have to worry about, in the end, the only distinguishing feature between them is the distribution of final state particles in the detector, and you need to implement a final state particle selection that will be model independent, but will maybe emphasize the aspects of the physics that's going on there that you really want to measure. So you have to, it's not sufficient to say, I measure diffractive events. You have to define what you mean by diffraction in terms of final state particles, for example. Okay, and that's what was done when we, as I mentioned earlier, when we looked at minimum bias and non-single diffractive. So I'm going to skip over this because I want to leave a bit of time for questions and just summarize the kind of the high level point of these two lectures. Really, I've gone into a lot of detail, which for some, on some cases, and I've brushed over detail in other cases, some of which you may need to drill down and worry about, some of which is just too much detail for some of you because you're not working on that particular thing. But all of it is based around this high-level view of what we're doing. What we're really doing is asking where to compare nature, where's the best place to compare nature to whatever ideas we might have about the way nature behaves. And we have choices to make. And we could, for instance, take the absolutist point of view and say, I am just going to compare raw data readout to whatever theory, to whatever expectations I have. There's no model dependence in that. You're just looking at electronic readout without even calibrating it properly. But if you want to compare to anything meaningful and learn anything from it, then any theory that you want to compare to has to follow all the implications of that theory through to final state particles and the full detector simulation, including the specific run conditions on the day and time-dependent calibrations and all kinds of other stuff. So in practice, this is just never done anymore. In some early, at least in collider experiments, in some early experiments, it could be done. And in some of the kind of more tabletop or low energy experiments, you can do this. So in a dark matter, actually in a direct dark matter search, this kind of thing actually is done sometimes, but not in a collider typically for the reasons above. You could compare to reconstructed objects. So this is where the detector, the experiment will have applied some calibrations, which may have some dependence on models. We have to, when we're calibrating, we do sometimes use nearly always use our simulations to interpolate from a test beam to the in situ detector, for instance. But those things can usually be controlled. They have very small model dependence typically, and the model dependence they have can be bracketed because you have enough standard candles and enough data that you can really make sure that your simulation is actually accurate to within some relatively small systematic uncertainty. So when you see like some of my earlier slides where I talked about the resolution or the jet energy scale or the jet mass scale or the electron energy scale, those are the kind of calibrations. How do we know what that energy scale really is? Well, it's through these calibrations, and we work very hard to make them as model independent as possible. So fine, that you can do it, but if you want to compare the theory to that, then you still got to follow all the implications through to at least some approximation of the detector resolution and efficiency. So you might use something like Delphas, which is a third-party detector simulation, but that's making some approximations that maybe not so well controlled. Or you have to hand your theory over to the experiment and they run it through their full simulation. So in addition to that, what you can do is this unfolding step, which I described earlier. So you invert the migration matrix that you've evaluated using your detector simulation, and you attempt to recover the fiducial final state particles. Again, that's usually quite well controllable. I mean, there's an extra model dependence built in through that unfolding procedure, but if you do it correctly, you can make it very, very small. You can make it effectively negligible. And what's left you can characterize within some systematic uncertainty. And the advantage of that is then that you can hand over to the theorist something which is just final state particles, which at least for a Monte Carlo prediction, you can just use immediately. You don't need to have any smearing or detector efficiencies applied. What the theory needs to do, of course, is predict the fully exclusive final state so that you can implement the fiducial phase space cuts on that, and you can implement the final state particle definitions. So you may want to go further. You may want to subtract the process or some intermediates. For instance, the vector boson fusion is an example of that. And the advantage for that is that the theory only needs to calculate that one process. It doesn't need a completely inclusive calculation there, and it doesn't need to apply the phase space cuts necessarily. So you can extrapolate to the full phase space, ignore and integrate over some bits of the physics that are difficult to calculate, for example. You may even go further than that. You may want the theorist just to provide you with some effective field theory parameters, and that would be, the experiment would then be fitting the measurements to the various cross sections which are sensitive to those parameters and extracting that. And the theorists really just need to think about how their ultraviolet complete theory runs downhill into a lower energy effective field theory. And in the end, of course, the final thing is we just correct to a full, we go all the way to an ultraviolet complete model, and all the theorist needs to do is have a good idea and then leave the rest of the experiment. So you make a choice about where you do those comparisons. I think, in my view, for the kind of physics we're discussing here, the fiducial final state particles is kind of the best compromise between model dependence and detector dependence, I guess, is what we're talking about. Although there are cases where comparing at reconstructed objects or EFT parameters or some of the other levels can be beneficial, I would say that having a fiducial final state particle measurement involved somewhere is usually the best thing to do. The final thing I'll just mention very briefly then is BSM searches. So they often don't unfold to detector level. You can unfold to detector level, and if you do, you can use them. And I'm involved in a program where we're reinterpreting some of these searches and measurements in terms of BSM theory. So a lot of these issues are flushed out there. My personal view is that the distinction between searches and measurements should become less important as we move into the high Lumi era, and in fact, as searches get more precise, they effectively have to become measurements. And you'll see, you saw the tutorials that Martin has been giving you on Contour. I hope some of you at least, that this can be really quite powerful. If you make the measurements model independent and you make the searches reinterpretable, then you can put them together and very quickly get information about new models without having to spend a year or two doing a dedicated search for them. I'm going to skip over the last bits, I think, and move to the summary. So what those were an example of a measurement, which is a model independent measurement that's very powerful for extracting searches. I can discuss it this evening, maybe, if you like. But in summary then, correcting carefully for detector effects is important to make measurements reusable and give them a shelf life beyond the experiment. And I would argue that that's even true for searches as well now. Make a measurement in a fiducial phase space, even if you do more afterwards. Think carefully about what you're measuring in that fiducial phase space. What are the final state particles? What backgrounds are you subtracting? And the overall goal of this, and the message really from both these two lectures, is to try and keep the data as clean and model independent as possible. So because we don't know, we'll probably only do one LHC, but we will probably want to be looking at the data through different theories, improved calculations, and so on into the future. So we want to avoid building today's theory into measurements that we want to be used for a long time in the future. And if we do that, then the rewards will follow, both in terms of demonstrating whether the standard model really operates well above the electroweak symmetry breaking scale, and also in terms of looking for physics beyond it. Thanks.
Great. Thank you very much, John, for this inspiring lecture series and message. Are there questions already right now?
I see at least one hand up. Is that Russ? Yeah.
Hi, thank you very much for the lectures. You mentioned that with unfolding, you introduce a model dependence, but you can make that model dependence essentially negligible. Yep. I wonder if you could just say a little bit more about how you reduce that model dependence, please.
For sure. In fact, the example I skipped over at the end was one of those, and it's a really good question. So the kind of thing I'm talking about is, first of all, well, the two things that go into unfolding are the migration matrix, which was that red arrow that I showed yesterday, right? So that you can control because you can look at, essentially that's measuring your detector response. So you do that through all kinds of standard candles, like looking at Z decays, J size, all that kind of business of calibration. Most of that is already in there, actually. So you've already, when you even at detector level, you have a calibrated jet. It's really that red arrow that's doing the calibration. So that's one of the things that goes into unfolding, and to a very large extent, using that doesn't actually increase the model dependence when you unfold. That's already there in the calibration at some level. The real nasty one is that obviously the migrations, say between two bins in momentum, don't just depend on the resolution and the bias of the measurement, they depend on the initial population, okay? So if you have a falling PT distribution, even if you've got a perfectly Gaussian response to PT, you have a lot more migration from low PT to high PT than you do the other direction, just because there are more events at low PT than there are at high PT. So there's an intrinsic dependence then in this unfolding procedure in what was the initial distribution. Now, sophisticated unfolding procedures, you see Bayesian style unfolding, iterative unfolding techniques done, they can get rid of that to within some understood bias by iterating and adjusting the input, the prior, if you like, if it's a Bayesian one, to get that right until everything lines up and you have a closure test and you can show that that works. So far, I've not described the real problem. Okay, all of those things you have to worry about, but you can deal with them. The real problem is if there's a variable that you're not unfolding, but that has an impact on the distribution. And a good example is, say, the B tagging efficiency, which can depend very strongly on PT, on the momentum of the B meson. But say that you're not measuring the PT of the B meson, you're just measuring the PT of the jet. Then the fragmentation function will tell you, what's the ratio of the PT of the B meson to the jet. If that's not well modeled, then your unfolding will be wrong, because the efficiency unfolding correction, the resolution correction you make for that B reconstruction will be wrong, because you're using a Monte Carlo sample which has a given PT distribution of the B, but the data had a different one. And so the efficiency in the Monte Carlo for B tagging is wrong. It's different, not because you've modeled your detector wrong, but because you've got the distribution of the BPT wrong. And the BPT distribution is not what you're unfolding, so the Bayesian unfolding thing doesn't help you, okay? So that's the kind of really nasty kind of gotcha in an unfolding thing. The way around that, there are multiple ways around that. The bottom line is you've got to really check that every distribution that you cut on in your analysis is well modeled. If that's true, then your unfolding will be working, okay? But that includes distributions that you cut on, like a B tagging, for instance, that you're not necessarily measuring. You're not directly measuring it. It's just part of your fiducial definition. If it's well modeled, if the efficiency is well modeled there in your Monte Carlo, then you can have confidence that the unfolding is working. If it's not well modeled, you might want to reweight it, or you might want to apply a correction first of all before you do your unfolding. And very often we do that. We have what we call a pre-unfolding correction, where we apply efficiency corrections that we know are strongly dependent on variables we're not measuring. We evaluate those separately, we apply them, and then we do the unfolding on a reduced set of cuts later. So all of those things, you can handle them, but all of that, of course, you can never completely remove this dependence. And so you end up with a residual systematic uncertainty. And you've got to have your eyes open when you do it. Sorry, that was a really long answer, but it's quite a complicated question.
No, sure. Thanks for the thorough answer. Thank you. Cheers.
Thanks. Any further questions? I don't see any right now. But as John said, we will have the opportunity again in the evening to catch up with the lecturers. So I told you earlier already that we have this special event, this Q&A session with the industrial lecturers. But after that, we can still break up into groups, or you can find the lecturer within the Gather World, the lecturers within the Gather World yourself. So I expect that this Q&A will last for at least half an hour. From experience, it's rather popular. So I don't know if you, John, if you show up at the half hour, it's probably fine, and then people can find you if they have further questions to the lecture. Is that okay?
Sure, I'll do that. Yeah, no problem.
Cool.
So show up at half an hour after the gather time starts. So
yeah, so 8:30 at Central European time.
Yeah. Okay. Cool. Good. All right. Thanks a lot, everyone, and enjoy the rest of the last day of the school.
Cool. Thanks to you, John.
Bye.
So everyone else, we'll see you again in half an hour for Marek's second part of electric corrections.